general, we don't. To start off, we assume that we know. We can do this stuff, and because the sign of this matrix is non-singular, we have some good properties. At the end of the day, what we are going to do, we are going to transform. We are going to estimate the model by OLS with this transformation in which we have the matrix. And we call this the GLS estimate.
So W was the matrix.
Okay. What is the problem? The problem is that in general, this W, this sigma square, sigma 1, 2, we don't know. So what we are going to do is, well, this is the feasible GLS, it's exactly the same, but applying this transformation, and we need many things. Sorry. Sorry here. Feasible GLS, we use an estimator of W, and we apply the transformation procedure. And this is the typical case. We are never in practice going to use GLS, we are always going to use feasible GLS. Instead of putting the matrix W, we are going to estimate the matrix and input it in the model. Okay. This is in general. This applies not only to parent data and not only to random effects. This is a different estimation procedure if we have something, because remember, the best thing we can do if we don't have extra information is OLS. OLS is superior to GLS. But if for any reason we have extra information and we know something about the structure of the variance-covariance matrix, then we can use this information to provide a better estimator because the weights are better. This is what is going to happen with random effects. But this is in theory. What happens in practice? That in order to do this with random effects, we need a lot of assumptions that are impossible. So first of all, so this is exactly the same model that we had before. First assumption, we need that both U and C are uncorrelated with X. So we are imposing this extra 1B assumption that before with fixed effects we didn't have. If this is not true, that in many cases is not going to be, then this is going to be inconsistent. But for the sake of explaining the method, let's assume that this is true. Okay, so we have this. Important, the GLS approach leaves CI into the error term. Remember, in the fixed effects approach, we were getting rid of CI. It was not in the error term, not in the equation, nowhere, because we were diminishing the equation. We were subtracting CI minus CI, 0. So we didn't have to worry about CI because it was no longer in our estimated equation. Here it is. And it's going to be in the error term, so the error term is bigger. So we need this. We need that X, the correlation between X and V is 0 for all periods. So contemporaneous, past errors with today X's, the other way around, everything must be 0. So it's a very strong assumption. This is strict exogeneity. But if this happens, then we can define W as the variance of this compound error. And if this assumption also holds, again, well, we should think if this is possible. In this case, it's more plausible than the first one, but still we have to think about it. We are going to have that the variance of U is sigma square of U, and the covariance between U and any other period in U is 0. So the variance of VI is just the variance of the sum of both. So we can very quickly construct this W matrix. And this W matrix, notice, the diagonal are the variances of the sum of C and U, and all the others as just the variance of C, because of the assumption of the sum. So it's very simple, kind of simple, because a very big matrix, we only need two things, the variance of U and the variance of C. So if we estimate these two parameters, we have everything. What is the cost? And we are assuming many things to get this nice expression. But again, if this holds, we don't have to worry about many parameters. It's just, we have to estimate all the betas plus two. Variance of C, variance of U. Again, if we knew these two parameters, we would have the GLS estimator, but in general we don't know it, so we are going to estimate sigma square of C, sigma square of U, and then we are going to use the physical GLS estimator. If we have, in addition, why not to assume more things, we have almost elasticity, then this is very simple, and then we are going to get that this is the beta random effects, that is just the OLS with the weights of W hat, and the variance is going to be very simple, and it's going to be just the usual expression of variance when we have OLS with this W included. But remember, we have been assuming these two things, almost impossible. We have been assuming this, we have been assuming this, and we have been assuming this. So, almost elasticity, no correlations, so everything like a very ideal world. In reality, it never happens. What I told you last week, I've never seen a paper with random effects. You can guess the reason why, because assuming all this stuff to get like this very nice estimator, it's far from being realistic. Of course, if this was true, so if all the assumptions were right, this is very powerful, because we are improving the OLS estimator by including a very nice variance covariance matrix. But again, it's
If you've never seen a paper, how realistic it is, how we actually find.
so. And this is why, in general, I tried in the last 2-3 years, I tried to not put too much weight on this, because it's that I wanted to show that it exists, but nothing else. So, if for any reason you see this in a paper, please first of all write to me and send me a paper, because I'm always saying that there is no paper, but maybe there is.
We have found a unicorn.
Exactly.
Read the paper and do the trash.
Okay, so then we have to do this consistent estimator of the things, but this is true. And then we are going to get this W hat, we do everything, and so on and so forth. What is doing Stata in reality? Stata is doing an iterative procedure, because most of the times it's not efficient to estimate only once, this variance covariance matrix. So what Stata is going to do is it's going to first estimate the matrix, then do the OLS with these weights, then update the matrix, then do OLS with the new weights, and so on and so forth until we find like the best one. This, of course, is done by the computer. It takes for Stata in a general model less than 1 second, but it's not like the first level that you have here is not the last one, let's say. But again, it's just a matter of the computer, and we don't have to worry a lot, basically because we are never going to use it. So in this case, it really doesn't matter. Okay? Sometimes we would like to know if this sigma square of C is equal to 0, so if this almost elastic, but we don't have variance in the C. Again, we are not going to use it, so it's not very, very useful. But if you see this with a Breuch pattern-test, you can kind of test it, but again, derive under joint normality, an extra assumption, so it's far from being a good application. So, How do we do this with this data? Very quick also. We have the same data set as the last day, so we have these roots, and we want to know the log fair, and the key explanatory variable is the concentration, and we also have the distance and the distance squared. And remember that what we call CI in this data is called UI. This is what we were doing the other day. Remember, with this command xtrect, we apply the fixed effect estimator. This is without any correction of the error term. So this is the good one with the cluster standard errors at the ID level. And remember, when we are doing fixed effects, this is good because we are getting rid of part of the bias, but this is bad because we cannot estimate time invariant variables. This is not a problem as far as this is not our main regression. So if we are interested in the effect of the distance on the log fair, we have a problem with fixed effects. If we want to estimate the effect of concentration, then we don't have a problem because the fact that we cannot estimate the distance is not an issue because everything that is time invariant gets dropped from the equation. How do we estimate this with random effects? We change this fixed effect by the option random effects. First thing you have to notice, log of this and log of the squared, they appear.
So for fixed effects, you use a drop in the effect of other variables. So random effect had the same
No.
idea?
No, this random effects is doing this with this W. So it's calculating the variance of U hat, the variance of C hat, and then it's computing this W hat, and it's introducing by GLS, by generalized least square, estimating this kind of OLS, weighted OLS with this thing, and it's doing an inference. So we are not transforming the data and then getting the OLS on the transformed data. We are doing in the original data, we are applying OLS with this matrix that is kind of weighting.
Well, what is the practical implication of using random effects? Like, I know the practical implication of fixed effect. I just want to understand.
The practical implication is that we can estimate time invariant components. Because here, given that we are not transforming the model, this is a good question, just to know what are the advantages and disadvantages of both. Advantages of using fixed effects. We decrease the bias, because everything that is time invariant disappears, no matter whether it's observable or unobservable. Disadvantages of fixed effects. That if we are interested in a time invariant component, we cannot estimate it because it's dropped from the equation. Advantages of random effects. We can estimate everything because we are not transforming the model, so everything that is time invariant, it doesn't matter. It's the same. It's gonna be in the model. Disadvantages of random effects, that given that we are putting everything, the bias is there. All the bias, time invariant and time variant. Okay? Again, we should do this with cluster ID. And notice here again, we're usually happy with concentration. The point estimate is the same, but the standard errors is increasing a bit. Well, a bit no, almost up. But the effect is more or less the same. Important with random effects. What happens if we do not control for distance in a random effects model? Like we were doing implicitly in the fixed effects. Notice the effect of concentration is very small, from 0.20 to 0.04. So it's decreasing by 4 or 5. So here the bottom line is, if you are using random effects, put in the regression equation everything, no matter whether it's time invariant or time variant, because if the variable is important, it should be there. So if distance in this case is important, it should be in the equation, because with random effects we are not getting rid of this time invariant.
I found a paper that uses random effect models, bro. For real.
In which journal?
Journal of Econometrics of Barranquilla. I'm kidding. Something like that.
Local newspaper of
Of El Congo.
okay. Well, remember that you can always publish paying.
I'm sure this guy's paid.
So again, so we shouldn't not include these time constant variables, but again, if we are not going to use in general random effects, we don't worry a lot. We shouldn't worry a lot about this. Okay, so we have pool OLS. This is just OLS with more data. Fixed effects. We are getting rid of all the time invariant components, observable and unobservable. Random effects, we are imposing a nice structure with the goals that we are assuming a lot of these to get this nice structure. Last method that we have for using panel data is first difference. First difference is very similar to fixed effects. Indeed, when we have two periods of time, they are exactly the same. But in some cases, it's going to be very powerful. We're going to see at the end of the slides. So first of all, the first thing we have to notice is that by doing the difference between periods, we are getting rid of CI. So again, with first difference, we have the advantage that everything that is time invariant disappears from the equation. This is why it's very similar to fixed effects. So we are going to estimate in general the change in y over the change in x and also the change in y. Notice we are going to lose one period because we are doing the difference. We don't have, so imagine the first period we have, we cannot make the difference with the previous one because we don't have. So every time that we are using first differences, we are losing the first observation. Let's say. The first observation in time. I mean, so if we have 7 periods, we are going to use 6. And then it's not a surprise if I tell you that first difference is going to be OLS applied to the transformer. So again, the same idea that we are doing exactly the same, and this is why OLS is very important, because we are always estimating things by OLS. The only difference is that we are transforming previously the data according to get a particular thing that we identify and that we are happy with this transformation. So, what are the assumptions that we need? Assumptions, first difference, the same as fixed effects. We need that only the time varying component of the error is independent of x. Again, this may be strong, in many cases it is, but it's less strong than assuming that u and ci are independent. Because here we don't have to say anything about ci because it's not in the equation that we are estimating. Because we get rid of this term by differentiating between periods. So we don't need to impose any assumption on the time invariant component of the error. This is very context specific. So if you are working in a paper, it may be the case that you think that most of the time of the unobservable components are time invariant, and in other cases you may think that most of the unobservable components are time invariant. So what I want to say with this is that it depends on the particular data set that you are working with, that it's more or less realistic that this holds. So that this holds. It's never going to hold directly, but you are closer to having this holding if you think that all the unobservable components are time invariant. Again, there is no way of testing this, but it's just if if you know very well the context and you know that very important things that could matter for explaining this relationship are time invariant, fixed effects or first difference are good methods to estimate them. Okay. In the paper that I'm going to show you after, with my market paper, I claim something like this. I'm going to say something like, if I control for all the things that I have, and I do this first difference or fixed effects model, most of the things that are left in the error term are time invariant, so are not related to the relationship that I want to estimate. Of course, this is a strong assumption, and I have to provide some additional evidence to prove that what I'm saying is right, but this is the idea. In some applications, you may say, okay, by controlling for a lot of fixed effects, I'm controlling for almost everything. And if this is not true, at least we are close to this situation. In other settings, this is not true. And then, even though you are using fixed effects, it's not enough. Because many of the things that you cannot control, because you don't have data or because they are unobservable, are time varying. And then the CI component is very small. When one thing is better than the other, it depends on the paper, on the data that you have, on the idea, on the context of methods. Okay. Second thing that we need, the standard thing, rank assumption. When we do the differences, we need variation in all the variables that we are going to do. So again, the same idea that with fixed effects. If we have time invariant components, the difference is going to be 0 for all the units, and then we are going to have kind of a missing row, and then this is not invertible, and we cannot estimate. In a state error, we never have this problem, because if we include a time invariant component, instead it's going to automatically drop it, and it's going to tell us this is dropped because of multicollinearity, but this is telling you that you are including a wrong part. If you were doing this by hand, you couldn't do it because you cannot invert a matrix that has no formula. As with fixed effects, no matter all the things that we are going to see today to have like nice expressions, we always have to make inference robust to serial correlation and to heteroscedasticity. So again, to cluster stuff. So very similar to fixed. With this non-robust form, we require an additional assumption. If we let E be the change in the error term, then we can estimate the model, and then we can get this nice expression. Again, this is non-robust. This is just to get a very nice expression for the error term. How many times are we going to use this expression? 0. Because we are always going to use robust and robust to heteroscedasticity and to serial correlation. But if we do like the standard thing of assuming that everything is nice, we get, this is the expression that we get for OLS. Sigma squared hat x prime x to the power minus 1. Sigma squared hat, the change in x prime, the change in x to the power minus 1. It's the same. We apply to the transform. But again, it's completely useless. Because if I've never seen a paper with random effects, I've also never seen a paper with fixed effects without clustering. The standard. Because this is one of the mistakes that it's very easy to avoid. It's just writing, so it's very simple to correct this mistake, and it's going to kind of avoid you many problems, like when presenting or when sending the paper to a conference or to a journal. If we want to get the fully asymptotic variance, so we get the fluorescence of the first difference, we apply this, and we get the standard formula for the variance of the first difference, but instead of having the x, we have the change in x, And here, instead of having you had, we have here. Again, I'm not very interested in that you know by memory these formulas because, first of all, you can check them, and secondly, you're never going to use them by hand to get any standard error. What I want you to understand is why we have to use one or the other, in which conditions. Okay? One thing we can do, and this is important, is that we can test for serial correlation. Under assumption 3, so under this assumption, against the error term yesterday. And if we are saying that this is kind of nice, we shouldn't find any relationships. So we can do a standard test of P1, and then if we gain that this parameter is significant, this is kind of an additional evidence that we should use robust variance matrix. One question, what happens if I do the test and this value is not significant? This parameter is not significant. Does it mean that I have to use, or that I can use any standard errors? Like, for example, homoscedastic standard errors.
To use heteroscedastic standard errors then, no?
Why?
To control, because of the correlation, significant correlation.
But if this is not significant,
You want to use that one?
we are saying that there is no correlation between autocorrelation between the error term today and yesterday. But I want to go to the philosophical idea of the test. If I don't reject something, does it mean that this something is true?
No.
Not
No,
necessarily. If I don't
not necessarily. I don't have enough evidence to reject it. So even if I don't have, so if I have evidence to reject, fine. This is what I was expecting. I have evidence to reject that this is not kind of independent in time, and then I have to use the cluster standard errors because they are autocorrelated and heteroscedastic. But if I don't reject, I cannot assume directly that what I'm writing in the null hypothesis is true. Is that I don't have enough evidence to reject it. So even if I don't reject, I cannot claim directly, hey, I don't have any problem here. The data is not finding a clear correlation between the error today and the error yesterday, but it doesn't imply automatically that I don't have the problem of autocorrelation. So at the end of the day, no matter what this test is telling me, the safest option is always to use cluster standard. And this is the problem that we have with tests in general, when the thing that we want to use is in the null. And this is why usually we design the test the opposite way. If we reject the null, then we are happy, because this is what we want to do. This is why we do this with significant test. If we reject that this is equal to 0, we can safely say that this is different. And then we are happy because this is significant. But if we don't reject, it's not significant, but it doesn't automatically imply that it's equal to 0, for sure. Okay? We can also apply feasible GLS to the first difference with the command xtg. It's kind of mixing the ideas before of random effects with these first differences. To be honest, again, this is something that I've never used. I'm not saying that in this case that it's possible, but I think it's not. It's kind of complicating things in a way that I don't see the point of doing this stuff. So remember, one of the main things you have to try to use in your research, if you do some kind of research or in your thesis for the master, is simplicity. So simplicity is an advantage. So if you are able to explain what you are doing to your real model, this is an advantage. because everyone is going to understand what you're doing. It's going to be. I'm not saying that simplicity is not the same that is wrong. That is even that is wrong. So you have to do things right in the simplest way possible. And these kind of things like mixing first difference that is very simple. It's just you are getting the data, you are subtracting one period to the previous one, and then you are estimating noise. When you complicate things through this GLS, you have to have a very, very good reason to do so. Because again, when you do feasible, first of all, GLS is not the standard language in econometrics. So everyone is doing OLS, and everyone is doing OLS for a reason. It's the best thing we can do, everyone is doing so we can compare things. So it's like we are talking the same language. If you change the language, then things are complicated. You have to have a very good reason behind to do this stuff. But in any case, if for any reason you have kind of this unrestricted variance matrix, you can apply this GLS correction to the first difference with this command. What is the disadvantage? Whatever you are going to get with this, you have to know how to interpret, what are the assumptions behind. It's not so clear whether you gain from changing the very simple stuff of first difference. But it's also possible, and I wanted to highlight because many times, and this is why I was telling you, this GLS is not unique to random effects. It's that GLS can be applied anywhere, like OLS. In the case of random effects, because we know the structure of W, if all the assumptions hold, then we can apply it like kind of right. But with the cost of having to assume a lot of things. More interesting for me is this idea of first difference and policy analysis. This is a very powerful method in policy evaluation. Imagine this special case in which we have only two periods, that we usually call before and after, and we are going to have a dummy equal to 1, indicating whether you participate in a program, like these treatment control groups. If we have this structure that the dummy prog is equal to 0 for everyone in the before period, and is equal to 1 only for those participating in the after period, we can estimate the model by the first difference, but notice that we are not differentiating prog because it's the same. The variable with the difference and the dummy is exactly the same because of the structure. If we have this is close to a difference in difference that we are going to review in the next class. Indeed, if we don't use these extra variables, this is a classic definition. But it's not the same that the definitive that we are going to see in the next class. Because in the next class, we are going to see a difference in difference more general. In this case, this is a difference over time for the same cross-section units. It's the same units. We are using panel data. In general, we can apply a difference in difference, which is in the next class, both with a panel data set or with a repeated cross-section. So we may have, for example, a survey, the European Social Survey, with some questions asked to people every 2 years. The people interviewed in the European Social Survey are not the same every 2 years. They are different people. So we cannot track the same individual over time. But we can apply the difference in difference, if we can exploit this before and after for any reason, to different people. So it's not a restriction that we have to follow the same people over time. In this case, this is more strict because we are following people over time. So this is the difference in difference to the same units. Important also is that if this not holds, so if we don't have this clear structure in which no one was obtaining the treatment in the previous period, and then some of units we're getting the after period. Then here we have to also differentiate the variable. So imagine that some people is getting the treatment in the before period. Here we should use the differentiated dummy instead of the dummy itself, because they are not exactly the same. But the idea will be the same. We can estimate this effect of any policy by using a first difference. So it's very powerful. It's very powerful because at the end of the day we can see first difference as a mix between fixed effects and definitive. And definitive in general is very strong, and fixed effects are very strong, and most of them are very good to combine them. So when we're going to see next week the generalized or two-way fixed effects, definitive, is kind of a first difference without real. So if you have a panel data, you can use fixed effects, you can use first difference, you can use definitive in some cases. And ideally, no matter the method, the estimators are going to be more or less the same. And one of the things that we're going to see at the end of this chapter is that if they differ, this is strong evidence that you have a problem of linearity. That some of the things that you are assuming that they are exogenous, indeed they are. And it's one way of checking whether your assumption that this time varying and observable component is not playing a real role. It's one way of checking if this is true is by estimating the assignment model by first difference and by fixed. If both are giving you more or less the same, of course, they are never going to give you exactly the same value, but close. If they are close, then you are safer that the method is more or less correct. Okay? How do we estimate in a data with first difference? We have two ways. First of all, we can create the variable, like the difference between period today and period yesterday. But I don't recommend this because you may have some mistakes. You have to, so imagine this with an Excel file. Imagine that you have, I don't know, remember you have this structure of data. This is ID, this is individual 1, individual 2, individual 3, measure individual 1, 2, 3. This is 2, 1, 3. If we want to do the change, remember this is going to be missing, then we're going to have so on. If the data is in this structure, we're going to have this right. But what is going to happen here, for example, in this line? Does it make sense, this? This difference here should be a missing value for the second value. So if we create the data set and we don't take into account these ideas, we are going to have some info
That is going to be misleading.
that is going to be wrong directly. So one way of solving this problem is not to create the variables, is to use this command that the state is giving us, is to regress with the differentiator factor. And then Stata is going to directly create this difference between all the guys, right? So it's not depends on our coding if we are doing this right.
Sorry, again, so that method is like you basically create each variable.
Exactly. So it's like generate the change in y as this value minus the previous one. But the previous one, you have to do it, you can do it, but you have to do it right. You have to sort the data, put the data in this structure, and then do it for each I, for ib equal to, so it's not direct.
Okay, and then?
And with this is direct. You don't have to worry about sorting the data, about creating the variables right, because this is going to be done directly by Stata. So in general, if you work with lags of the variables or with the difference of the variable, with this d dot and the equation, or l dot if you want to use the lag, directly in the regression is quicker. Okay.
Prof, and in that command, how do you group? Like if I want to group, no, but you have to group by ID, of course. And which is the ID there?
No, it's because this is the advantage here. We don't.
I don't need to put ID.
Well, the only thing I have to do is to declare the panel data. X is set, and then I'm writing ID is my variable of like the individuals, and year is the time variable. So ID and T would be in this case. And if you tell this to Stata, and then you regress this with the d dot function, Stata, because it's knowing that you have this panel data structure, is going to do this directly right. So you don't have to worry about I made this mistake. No, it's not direct. Okay. When we do this difference, this 0.17 is very close. It's close to the first fixed estimate. So, and the p value is the same. So it's very simple. Remember, use the cluster ID, and then all the estimates are very similar to the fixed effects. That is good in general. Okay? What I was saying before, we can also do this test of autocorrelation. We create the residuals, and we estimate the residuals with the lag of the residuals. And again, I don't have to create the lag of the residual. I just write L dot the residuals, and I get this value. And in this case, the p-value is 0.30, so we don't have evidence to reject that they are not serially correlated. But again, finding that we don't have significant evidence of no serial correlation in the first degree doesn't mean anything. We still have to use cluster ID and this thing. Okay? Last two things. Comparison between estimators. So first of all, between first difference and fixed effects. If we have two periods, they are identical. So in a setting in which we are using this before and after just with two periods, it doesn't matter whether we use first differences or fixed effects. And this is the way we are constructing the fixed effects. It's just the fixed effects is that the difference between the value and the mean. The mean in two periods is the same. If we have more than two periods, which one is more efficient or is better is going to depend on the error term. So fixed effects is more efficient under assumption fixed effects 3, so that UI is serially uncorrelated, and first difference is more efficient if UI follows a random wall and then the change in UI is serially uncorrelated. What happens in reality? That the truth lies somewhere in between. So it's never going to be the case, or almost never going to be the case, that UI is uncorrelated or the change in UI is uncorrelated. Many times it's kind of inevitable. So in practice, what do we have to check? That they are, what I was telling you before, that they are more or less similar. Because if they are very different, both are inconsistent, because this is a clear evidence that the error, or that we have some endogenic problems. They may be because of measurement error, because we have time varying omitted variables, because of time, all the things that we know about endogenic. So the first thing you have to do, if you have apparent data and your main strategy is using, I don't know, fixed effects, well, let's estimate this also by first difference and check whether my results are consistent. If they are consistent, you cannot be sure that everything is fine, but at least you have some guidance that it's plausible. If they are very different, it might that they change significance, they change the sign. It was like, I don't know, 20% percentage and it goes to -3, these type of things, then you have a problem. Because it's something behind that you are not controlling that is biasing both your fixed effects and your first effects. You can also do a formal consistency test, and it's basically doing this first difference equation, including one of the regressions without differentiating. And this gamma shouldn't be significant in the first difference equation, because if this is right, everything should be here in the limits. But again, these type of tests usually are very based on very strong assumptions. So I'm going to show you in the paper other things that you can do if, to convince people that your method is right, rather than, because rejecting or not rejecting this is not going to give you enough power to say that something is right or not in most applications. So you cannot convince people by saying, hey, this I was doing this test and it's not significant. It's not strong enough. It's there, but and if it's fine, you can include it in the paper. It's not enough. Finally, first effects versus random effects. What is the only reason why we should use random effects? Basically because we have imprecise fixed effects when our main regressor varies over time, but not too much. So we are going to get some variation that implies that we can estimate this effect, but very precise. This is the only reason why we should think about using them. The essential distinction between them is that, of course, random effects is inconsistent if the effects are fixed and the other way around. Random effects is more efficient if not. But the random effects, because here in the fixed effects, remember we are only using the within variation, so we are explicitly getting rid of some of the variation that we have in the model. So the variation is smaller, precision is not also smaller. But we are, there's always, remember, a trade-off between precision and bias. And what is more important? If you have to choose, do you prefer to get more precise estimates with more bias or less precise estimates with less bias?
Less precise estimates with less bias.
The first thing is the bias. So first thing we have to get, consistency or unbiased. And then we could worry about whether things are more or less precise.
And that's why the reason behind that is because when the sample tends to infinity, you cannot eliminate the bias, but you can eliminate, so you can get more
Precise, exactly. This is the formula of the standard errors, because here we have to distinguish two things. One thing is to get the betas. To get the betas right, unbiased or consistent. Another thing is how precise these betas are. It's beta hats.
It's a trade-off.
and this is a trade most of the time. But they are independent. You can get some betas are very precise, some beta hazards are less precise, some beta hazards are very precise but are not consistent, some beta hazards are very precise and consistent. So it's not the same issue, because one thing is how do you get the betas, panel data, IB, OLS, full OLS, RDD, DFID, some estimation strategies. And another thing is how precise these beta hazards are. And this depends on the sample size. The bigger is the sample size, the more precision you are going to get. The variation in X, the more variation you get in the X, the more precision you are going to get. And the variation in U, in what is left behind. And in this case, it's the other way around. The more variation we have in U, the less precision. So, again, here you have a method also to test whether CI and XI are correlated, and this is also the Hausmann test. But again, this is something that in practice we never apply because we never use. So this is kind of a way of saying, okay, if CI and XI are uncorrelated, then we can use a random test. But like in the previous test, it's not enough. You can conclude in this test that they are correlated, but it doesn't imply that they are correlated, and you are going to have also many other problems. This is why in general random effects is not a very solution. Okay. So we stop here. Questions regarding this? Let me then go to the paper. Okay. So first of all, before going to the paper, let me tell you a bit about this idea of PhDs. I don't know how many people here is interested in PhD. I know some of you are. The path of doing a PhD is quite hard, but also rewarding. It's not for everyone, I would say. Is of course I'm biased here because I did it and I'm here, so I try to be very kind of objective, but of course I'm in one side clearly. It's complicated, first of all, for one main reason, for me at least, is that we are used to, as students, as receiving information. Can be more or less difficult, you have to study more or less, it would be more or less problematic to understand, but it's only like you are a basic agent. You get something, you try to learn, then you show your knowledge in an exam, in a presentation, in a report, whatever. When you are doing the PhD, this is completely different. You have a blank piece of paper, and you are the one in charge of filling this piece of paper. And it's kind of exciting and at the same time kind of strange feeling. So it's something that you have to kind of love, because it's a mix of creativity and intelligence and this kind of things. Okay? In my case, I was doing the PhD in Alicante, and I started basically having no clue about what I was going to do with the PhD. I did a master, like the MEP, similar to the MEP, 2 years instead of 1. I got a scholarship, and And then it was like, okay, then we were in the middle of the 2008 crisis. I'm getting some money, so why I shouldn't continue this path if I'm getting some money and at the same time I'm kind of improving my CV. But when I started the PhD, it was like, wow, how do I do this? In my case, I had luck and I had very good advisors and they were very patient with me and they were kind of teaching me how to do research. This is possible. And I started with a different paper, not this one. I started with some things in Bolivia, pension system. We will discuss this in the next class with RDD. But it was not my area. But in the PhD, one of the main things you have to do is what we call the job market paper. The job market paper is the paper in which you show your skills, let's say. And ideally, is the one that you are going to show to the world in what we call the job market. The job market is once you finish the PhD, you think that it's over, and it's not over. It's the beginning of something that is even more stressful than the PhD itself. That is trying to get a job. And in order to get a job, you compete with all the other PhD candidates from all over the world in a kind of centralized system in which universities, central banks, institutions are looking for new PhD candidates, and the PhD candidates are looking for a place to work. So your job market paper is basically your main tool that you have to convince universities, institutions, central banks, whatever, that you are the guy that they need to have. So it's a very strong part of your doctorate. In my case, I was kind of tied with this idea of Bolivia. I wasn't really interested, so I changed. I had surgery in my knee. I have 1 month without walking, so I invested my time in reading a lot of papers and thinking about, okay, how can I do something that I really like and that I can motivate myself and do something that's meaningful. And I got an idea that mixing many things that I was reading about one thing that is called partisan alignment, the same parties ruling different layers of government, and corruption. I read some papers about corruption, I read some papers about partisan alignment in many countries, but no one was kind of mixing these two ideas. And then I thought, okay, can I try to put this in context in Spain, because I know that there are many corruption cases. At that point it was 2013. It was like huge of corruption scandals everywhere around the Mediterranean corridor, in Madrid, in Galicia, many places. Many parties, everyone was involved basically. So I'm gonna go first for this corruption database. So I was checking one by one news in reports, in newspapers, in forums, wherever, and I was like using this. And then I got, just by reading, 683 cases that I wanted to. I read more, but some of them were like, hey, you are corrupt, without anything behind. So you have, first of all, you have to distinguish whether something is real or not, and it depends on you. Sometimes it's not clear, sometimes it's just a negotiation of whatever. But under my criteria, I identified 683, and I had like 3 electoral cycles. From 1999 to 2003, 2003, 2007, 2007, 2011. For this, I was identifying who was the guy doing corruption. could be the mayor and some municipal councillors, in addition with others, in addition with the mayors and others, only municipal councillors. Other times it was directly like the city hall, the ayuntamiento doing something wrong. And in few cases it was other, I don't remember to be honest, which these 5 cases were, but it could be something like, I don't know, someone not related directly to the local government.
Hi.
Here we have I also identified what was the main issue behind corruption, because we can have like bribery, prevarication, fraud classification, and urban fraud, 3 crimes combined, 2 crimes combined was like a mess, many things. Again, also by distinction, and also here I also try to classify the stage in the judicial process. It was just reported in the news, it was investigated, it was a formal accusation, someone was convicted, and here notice that there is a lot of variation. So it's not because the judicial system is quite slow. From the first time you know something about a scandal case in the news until someone is charged with some particular fraud or whatever, it may take 10, 20 years. So at that time, it was not clear what was going to happen with some of the cases. And this is important because when you are talking about this type of scandals, it's not the same to have a scandal to have a real corruption case. So one of the things that I did at some point was to, okay, if my specification that I'm going to explain in a few minutes is robust to include only those that are accused or convicted, so if I select only the subset of real, very real or strong cases, because they are already in the judicial system, and here, for example, someone is convicted, so it's kind of really proven that is a real corruption scandal. Is what I'm intending to in my paper is the same. So this kind of things, when you are self-constructing your database, you have to think in many details that, to be honest, I can explain to you today because I did this in the past, but when you are starting, many times you don't even think about it. Because it's not the same to get your own data that you get the data from any data store that is available. Good news about having your own data is you can construct it, so it depends on you. Bad news is that it depends on you, and then you can make mistakes. Sometimes when you have data, for example, what I was telling you before,
Yeah,
you
near
cannot
the
do
center,
anything.
Near what?
near the center of the city.
I would like to have this additional info wherever.
I'm gonna show
It's
you
on there.
later.
It's on
I'll
there.
show you, okay?
Your power to change this is 0. When you are self-constructing your data, you have more power, you can decide things, but at the same time, it depends on you, and if you are in a very early stage of your career, you may commit some mistakes because you are not smart now, or you don't know anything, or you are still
Building human capital.
investing in your human capital, exactly. Okay? So, then let's go for the so first of all the
So that data that you showed, you created or you got it from?
I created.
Oh, you created your own data.
So I was checking case by case, reading. Of course, it was easy because it was in Spanish, so it was kind of not easy because sometimes it's not easy to understand the concepts. But this one in your own language, so it's. And I was creating an Excel file with all this information.
And you were classifying on your own whether that's like conviction, whether you were. I mean, if you're convicted, it's easier. You have a
Exactly.
But then, if
But you have to read. You have to read in a newspaper, and then you read it, and then you feel
I'm
kind
saying,
of.
but that's on based on your own criteria. I mean, besides the whole conviction, because you have a sentence periodicity
Exactly.
at the end, the other four, you have to use your own
Exactly.
common sense / criteria.
And so spoiler, I started this in 2013 and it was published in 2021, so 8 years after. So one of the things that I did wrong at the very beginning was I read everything, but then in my database I only got a dummy variable equal to 1 if I have a corruption scandal, equal to 0 if not. So all the information that I was reading was nowhere. Because I didn't realize that it could be. And at some point, after sending the paper to some journals, after talking to people, I realized that all the information that I was presenting right about this convicted, not convicted, in which period, if it's the mayor, if not, whatever, I should put this on my database. And then I have to go back to all the things that I had, to reread again everything, and update it, and then I expanded my Excel file by writing, okay, it was nice because some of the cases, when I read it at the very end, like, 5 years before, I didn't have information about how it was evolving, and after 5 years, I have more information. So I could update some of the cases. But it was like, I have to reread everything and then include in my database, okay, this is convicted, this is not convicted, this is the mayor, is the city hall, is the one, is the other. So typical mistake that you make when you are starting the business and you are investing a lot of time in creating something, but at the same time you are just focusing on one variable when you could have many of them. So just to understand a bit what we are talking about, in Spain we have basically 3 layers of government: central, regional, local. We have over 8,000 municipalities, although 90% are below the average number of inhabitants, so it's a very small municipalities. The main player is the local government, and we have a big discretionary power of mayors. They can even set their own ways, for example. Typically, this is the first thing they do when there is a new mayor in a municipality. I was talking about in the campaign about people, but the first thing I do is to increase my salary. Typical case. What is the electoral system in Spain? We have local elections are the same day in every municipality in Spain every 4 years. Usually in May. May 2027 would be the next one. Regional elections at that time were held also the same day as municipal elections in 13 out of 17 regions. Today this is a mess. Probably in 2027 we will have like 4 or 5 only regions at the same day because some of the governments are anticipating elections, but there are many things. At that time it was more stable, and the only 4 remaining were Andalusia, Galicia, País Vasco, and Catalonia. We have a close list proportional system with the home rule, and we need at least 5% of votes to get a seat in the municipality. So if you get 4.99% of votes, you get a 0 there. And then, important, mayors are elected by a majority of the council. So it's not like in the US, for example, if you win the elections, it doesn't mean anything. You can win the elections and not be in the mayor. Or your party can
I'm
win
so
the
sorry,
elections.
can you explain that to me? Because I mean, I have no idea about
Okay,
that.
so-
That sounds so weird.
Exactly. So you get, because it depends on the number of seats. I'm going to put a very simple example. There are 11 seats. The first party gets 4. The second party gets 3. And the second party gets another 3. And there is one party with 1. And let's remain with that. The second and the third party can get a coalition. They sum 6. They have absolute majority. One of them is going to be in charge of the local government.
Yeah.
Even though the first party got 4.
Like here in Spain, we don't elect the government. We elect the
The-
parliament, and the parliament elects the government.
Exactly.
Oh, we can't do that in Peru.
So basically, for example, here, if I'm correct, PP has more votes than PSOE in the national
In the
scale.
national.
And is PSOE the one that governs?
And there are many municipalities in which PSOE won the last elections, but PP and Vox have a very good
Okay,
relationship.
so I go against Pedro, he told me the votes, and then I went, my party went for the seats, and I ended up losing. That's how it works.
Sorry, repeat?
Like, he wins, like, by number of votes.
Yes.
But my party is the one that have more seats.
No. If he wins, he has at least the same number of seats than you, if not more. But given that there are more than two parties,
I can do an alliance.
exactly.
Oh, okay, get it. Like, instead of somewhere we have two parties.
Exactly. So most of the times they are ideological allies. So the right goes together, the left goes together. Most of the times.
Okay.
But there are special cases in which you can have kind of strange alliances.
Vox and
Vox and
PSOE.
PSOE, for example. Something like this. It could happen because, especially in small municipalities, because it's kind of parties and
And
also.
so those seats elect local municipalities, mayors, and what else? What else are elected that way?
It's the mayor, and then the mayor selects like the council.
Oh.
Like from the councillors that they have. So you're gonna be my, I don't know, my councillor of economy.
But the mayor is elected by, you said, like the parliament, right?
Excellent. Important thing, just to clarify this, if in the first voting, these parties, no one is elected with absolute majority, then the mayor is the one of the most voted party.
So let's complicate.
It's very complicated.
This is like.
It's very complicated, and one of the things that is very complicated for researchers is that it's not so straightforward, by far, to identify who is ruling by observing who is winning. This is as a researcher, this is my main problem. That I cannot infer directly by looking at the elections who is ruling. Because anything can happen. The only cases in which I know what is going to happen is if one party has absolute majority. So if I have 11 councillors, 11 seats, and one party is getting 7, then it's fine. Because no matter what the others can do.
So you care more about the seats than the actual.
Exactly. The seats is what matters in Spain. So it's very complicated for researchers to use this because it's a mess. Typical case that in the States they are doing with this stuff, they use what we call a closed race RDD. A regression discontinuity design comparing municipalities in which one party won by a small amount compared to one party which is.
But I suppose the president doesn't work that way.
Yes.
For the president also you can have majority and then.
Yeah, indeed we have this now, right now, this case.
That's mind blowing to me. Okay.
This is
Welcome to Spain.
okay. So I finish with it and then with the break. So we have 3 consecutive local electoral cycles, as I told you. These correct practices at the municipal level that is constructed. My outcome of interest, this is what I was telling you, this is dummy equal to 1 if I have a corruption case in the municipality in one of the 3 elections, and it's important, it's not a corruption scandal, so I don't care about when people knew this. I'm caring about when this occurred.
Question on the data. So when you submit your paper with the data, the referee, like, will have to do some due diligence on your data, right? They'll have to go grab your data and then, okay, I'm gonna randomly select 4 cases to see if your judgment is.
It's-
How do you, like, because it's not like, okay, I downloaded data from the Central Bank of Spain and has some sort of. You know,
Yeah, completely
It
right.
could be not just you, it could be anyone, right? And then I just write data, and maybe you have a similar paper with similar data that I created. Let's say my criteria was different than yours.
Exactly.
And how the referee approaches that.
It's up to them, but I think one of the ideas would be this, like to select something and check whether this is consistent if you check by the 2 or 3 cases that you check that you see something strange, if you don't see anything strange, at that time, other people were doing something similar. We had like kind of similar database with this small difference depending on the criteria. And one of the things they told me where you are investing a lot of time in creating this database, this is kind of directly a contribution to the paper, but you have to explain better what you are doing, what you are getting, where are you getting from. So it was like, at the beginning of the paper, it was like, I've done a lot of stuff, but in the paper it's only my outcome and few things more.
And then someone else can use your data, right? That becomes part of the data they can use for other papers.
Yes. And then, well, I have, so I tried to complement the news with I was using two corruption studies carried out by El País, which is kind of the main left-wing newspaper in Spain, and El Mundo, which is kind of the main right-wing. So just to try to get a balance between, because many times, or one of the potential threats you can have here is that you are biased and you are getting only the cases that pointed out by one side of the ideological spectrum. So I was trying to compensate kind of, it's not a matter of who is pointing out the politician, it's a matter of that indeed it was a case. And then I mixed this self-constructed database with the local and regional elections coming from the Ministry of Interior. And my treatment variable, I defined the treatment variable as a dummy equal to 1 if the same party was ruling, not winning, I don't care about the outcome of the election. I was able to observe who was ruling, and then if it's the same party ruling, the local and the regional government, I got a 1 treatment. And see what it. So I have the parting power at both levels, the minor saying in municipality. I was also able to observe if there was changes in the municipality, because sometimes we can have like a censor vote at the middle of the municipality, at the middle of the term. And there are many things that can vary. It's a mess. So, but I think I could control for almost everything that at least was observable. And this was the map of corruption scandals. In blue you have PP, in red you have PSOE. The bigger, so PSOE is kind of the main left wing, PP is the main right wing, and the size of the dot implies that you have more corruption scandals by term. So the bigger one, like for example this one, or this one, is that you have a corruption scandal, different corruption case in each of the 3 electoral cycles in the same municipality. So I have here, I'm from Alicante, here we have in Benidorm, for example, or in Orihuela, I'm from Orihuela, a town in which we have the record of convicted mayors in Spain, like the last 5 were in jail or close to being in jail. they look like the president.
Yeah. The last 6 presidents in jail.
So notice that corruption is where the money is. Madrid, Mediterranean,
Of course, Granada has been
the coast. So in Soria, here is
No, no, no como Granada y Sevilla, sí.
Mira Extremadura y
No como Granada y Sevilla, sí.
there's nothing. Not a surprise.
hasta el alcalde está llevado.
Casi todas, en Sevilla casi todas son naranjas, pero en Granada tiene naranja y de repente una azul ahí en medio.
Sí.
So it was an interesting case. So let's stop here, 20 minutes, and then after the break, I tell you about the strategy and how I solved the problem of la pressure.
Creo que los temas de
Al alcalde de mi pueblo te ha robado dinero. No te pases por la calle, no sé qué años. Robando bandas, pasando Da igual, porque yo no le cojo y Tienes una parte que ¿qué pasa? Traigo